Okay, so we're going to talk about control of breathing here with regards to exercise, and so this is going to be pretty brief, but I'm just trying to give a basic overview here. So there's a couple of different ways that ventilation can be affected, and exercise can play a huge role in this. So to start off, I want to talk about the chemical and the neural control of breathing. So first of all, let's talk about the chemical control or chemo control. So with chemo control, we're looking at the chemicals that are in our body, specifically carbon dioxide and oxygen. So generally speaking, oxygen is sensed in the peripheral chemoreceptor, whereas carbon dioxide and hydrogen ion are sensed directly or indirectly in the central chemoreceptors. Remember, hydrogen ion can't cross the blood-brain barrier, but CO2 can. When CO2 combines with water, that forms carbonic acid, which then breaks down into bicarb, which usually ends up in your cerebrospinal fluid, and then hydrogen ion, which can be sensed in by the central chemoreceptors. So high levels of CO2 cause high levels of hydrogen ion to be produced in your brain. Okay, and so if we have high levels of CO2 or hydrogen ion and or low levels of oxygen, that will stimulate the respiratory centers in your brain to increase ventilation, right? So they're going to signal the diaphragm to breathe more. Now, similarly, we've also got the neural control. And with neural control, we've got stretch receptors. And so notice here, we've got these stretch receptors in our lung. And so it's a negative feedback loop. And so what happens with this is that if our lungs are really filled, we're actually going to decrease ventilation. Okay, we're going to try and get that air out of our lungs, right? Just imagine taking a breath of air in, so you fill your lungs all the way up. Now try and breathe normally, but at that lung volume. It's not very comfortable. It's not something anybody wants to do, and so we don't do it. And the reason we don't do that is because we have to generate so much pressure to get air inside of our lungs. There's a reason we breathe at the lung volume that we do, and it's because it's in a optimal place where we don't have to generate a lot of pressure, but we can increase our lung volume quite a bit. Okay, and this is on something that we might see later in the semester called a compliance curve. All right, so we've got chemical control and neural control. Well, interestingly enough, we get information from other places besides these chemicals and these neurons. And from these stretch receptors, we also have receptors in our muscles. Okay, and so we get afferent feedback from our muscles, and that also affects how much we breathe. And so the greater the afferent feedback we get from these muscles, the more we'll breathe. Okay, and that should make sense that if our legs are going or working really hard, like when I go run later today, I'm going to have more afferent activity, and as a result, that lets my lungs know I need to breathe more. And so that's what happens. And there's this study by a colleague of mine. His name's Marcus Alman. He did this over 10 years ago, which is kind of nuts. That 2010 is that long ago. And what he did is he had subjects complete 2 exercise bouts riding a bike. One was with a placebo, and the other was where they received fentanyl. Okay, and yes, that fentanyl. So it's an opiate. And what this does is this basically decreases the information, or it's a blockade on those afferent neurons. And what they found was that in the condition where they had fentanyl, the ventilation, they were hypoventilating because they weren't getting as much feedback from the exercising leg. And so as a result, exercise was not as good as it could be. So with breathing, when it comes to exercise, we're getting information from oxygen and CO2, or about oxygen and CO2, which will affect our ventilation. The stretch receptors in our lungs will cause changes in ventilation, and then also afferent feedback from our muscles.